Hi everyone! In this video, I will introduce the famous Black-Scholes model. The original paper presenting the model for the pricing of options was published in 1973 by Black and Scholes. The model led to a boom in the derivatives market, and both Merton and Scholes received the Economic Nobel Prize for their work in 1997, while Black, who died 2 years before, was mentioned as a contributor. Here are the main assumptions of the model. Markets are random, markets movement cannot be predicted, and we assume that the underlying stock price follows a geometric Brownian motion. Stocks are not paying any dividend. We can trade continuously with no transaction costs. There is no limit on short selling with no borrowing constraints. The risk-free interest rate is constant, and there is no opportunities for arbitrage in the market. We assume a financial market with two assets, one risky asset such as a stock price and one risk-free asset such as a bank account. We assume that the stock price ST follows a geometric Brownian motion with the following stochastic differential equation, WT being a Wiener process, mu is the drift, and sigma the volatility of the stock price. So ST has the following expression. It follows a log normal distribution. We simulate here 10,000 paths with T equal 5, R equals 3%, and sigma equal 20%, and show on the right the distribution of ST at maturity. We assume that there is one risk-free asset PT with R the continuously compounded risk-free interest rate. So 1 unit invested in the cash account at time 0 will worth exponential RT at time t. And we consider a third asset, an European contingent claim, so typically an option, on the risky asset S. We know its final price at maturity, its final payoff, and we want to know the price P of the contingent claim at any time t. For that, we consider a self-financing portfolio pi. It is short one option, its initial value being minus P. It is long the underlying stock in a quantity equal to the partial derivatives of P with respect to S, and we borrow in cash the sum of the two in order to finance the strategy. So the initial value of the portfolio is equal to 0. Here are the quantities that we have on the three different assets. And we calculate the variation of the portfolio on a small interval dt, assuming the quantities do not change. dB is equal to R times B times dt. And for dP, we apply the Ito lemma, and we get the following expression for the variation of the price of the option. So we replace dP and dB with the corresponding expressions. We see that the terms in ds cancel each other. By purchasing a quantity equals to the partial derivative of the price with respect to S, we are able to cancel the risk related to the risky asset in the portfolio. So we get the following expression for the variation of the portfolio between t and t plus dt. There is no random term, so it is a non-risky portfolio. By no arbitrage condition, its return is equal to the risk-free interest rate. As the initial value of the portfolio is equal to 0, the variation of the portfolio is also equal to 0. And so we get the following equation, which is the Black-Scholes partial differential equation. We remark that there is no drift component. Any European contingent claim satisfies this equation, and we were able to find a hedging strategy offsetting the risk in the portfolio. With boundary and final conditions, this equation can be solved numerically to determine the price of the derivatives, with closed-form solution in some cases. For example, for European call and put options, the boundary and final conditions are determined by the payoff of the option. And the equation can be solved analytically with closed-form solutions. For more complex derivatives, numerical methods have to be used in order to price the products. Thank you for your time.